think today we'll start off. Whatever we can do, we'll try to. I'll start sharing. Sort of discussing the second chapter today, alcohols, phenols, and ethers. So basically, as we'll just move fast. Again, this chapter deals with three different classes: alcohols, phenols, and ethers, and deals with all classification, nomenclature, preparation, properties, uses, and all that. Learning outcomes. I think when we put out the PPT, we'll do, because everywhere it's same. Let's not waste time. I'd put up a few questions of yesterday here. If a few, one or two at least, we'll just discuss of converting 2-bromopropane to 1-bromopropane. It's very simple, just previous board questions. That's all. Thought we'll just discuss of as what we discussed yesterday. 2-bromopropane to 1-bromopropane. So what are the steps which we take up for converting this? The same haloalkane at different position isomer to be formed. So what possibility do we go in for? Yes, teachers. Anyone?
Elimination and addition.
Yes, CHBr and CH3 coming in. So first we go in for elimination. We convert it to a alkene. As discussed, alcoholic KOH, and followed by, now we are to get 1-bromopropane. So here addition of HBr, there it comes out to be. So it's a 1-bromopropane that we have to add on, that comes in. So it'll be HBr addition. What is missing there? What is? It should be in presence of peroxide. Anti-Marconic of addition comes in. So that's all, a very simple conversion, very simple, where children can score very easily this type of questions. And I just put on this one is because, again, we have to instill in children about the ortho-para directing groups, activating groups. So benzene, when to be converted to para-chloronitrobenzene, both chlorination and nitration. So how do we tell the children about introducing which first? That comes in. That's a very important part whenever such type of conversions come in. So how do we go about this one? Benzene to be converted to para-chloronitrobenzene.
Nitration and then chlorination.
Ma'am, why do you think it's nitration followed by chlorination? Not. We have two steps to be followed, yes. One, we have to introduce nitro. One, we have to introduce chlorine. Can we have any possibility, any order, or we have to stick to a specific order? So if you say nitration, ma'am, nitro group NO2 plus when comes in. NO2 is what type of group when it comes?
Electron withdrawing.
It's an electron withdrawing group, ma'am. So ortho-para directing or meta directing?
Ortho-para. No, ma'am. Electron withdrawing group.
It is not an ortho-para, ma'am. NO2 is electron withdrawing.
Yes.
So ortho-para positions become less in electron density.
Meta.
So it goes for meta. So here we need, it is in 1,4 positions, the introduction. That means it's with respect to each other, it's para. So nitro, if you go in and then chlorination, chlorine will go into the meta position, is it not?
Yes.
So we'll have to first introduce
chlorination.
Chlorination, and whenever it's on the benzene ring in presence of anhydrous aluminum chloride, that is another thing we have to stress. So we get chlorobenzene, and then we go for nitration, concentrated HNO3 and H2SO4 mixture, nitrating mixture. So this gives us this. So this one particular, this type of questions, or it should be meta-chloronitrobenzene, we go in the other way. So this, no, which is different. So that is why I thought always children
Depends
get
upon
confused.
the orthopara directing only, or is there any order, ma'am? Like this.
Which one, ma'am? Yes, ma'am.
Sorry, ma'am. Is there any order, or depends upon the directing, meta or para?
Directing group, ma'am. It's based on directing, the nature of the group.
And then the depends upon the product.
Yes,
Para
what product we need based on that, whether it's ortho para directing, meta directing, we go in. So most questions of these type will be like that, no? Based on that. So on that, if both are ortho para directing, you want to get a product, something related to that, now we can have any group introduced first. So there's nothing else. In all these, I think that's fine. And if we discuss at least one question from this part, rearranging the compounds. Suppose we go in for the second question, 1-bromo 3-methyl butane, 2-bromo 2-methyl butane, and 3-bromo 3-methyl butane. It's SN2 displacement. So which will be the order? One bromo, and we have a methyl group in position 3. Second one is 2-bromo 2-methyl butane. Just what is required. And the third one is 2-bromo and 3-methyl butane. So they've asked for an SN2 displacement, ease of SN2 displacement. So which one will be the least reactive towards SN2? Yes, ma'am. Yes, sir.
First one will be more reactive. Am I right, ma'am?
Yes, ma'am. Yeah. Right.
Because it is primary.
Yeah.
And then 1 minute, ma'am.
Yeah.
Then the last one, that is secondary, no?
Yes, ma'am. Right.
And then the second one.
Yes, this is the least reactive. No? The middle compound is the least reactive. Yes, right, ma'am. So that, yeah, that's the thing. So these we go on like that. We explain to the children all this textbook only. And the last one here, we have the 3 sets of compounds, and they've asked you again, which is most reactive towards SN2. So again, it's SN2 mechanism here. We have 1-bromo, 2-bromo, 2-bromo, 2-methyl. So very simple sets for SN2 identification.
1-bromo.
Yes, so the first answer goes in for 1-bromo pentane, right? The compound which is optically active.
We have to write down the structure.
Yeah, we have to write and see. That's what. Optically active compound.
2-bromo.
2-bromo or 2-bromo, 2-methyl butane that comes in.
1 minute. Second one, ma'am.
2-bromo 2-methyl butane, ma'am.
2-bromo 2-methyl butane.
Yes, ma'am.
Will it be?
Yes, ma'am. Because
Wait, ma'am.
1-bromo and 1-methyl.
No, sir. Second one, 2-methyl group will be there, no, around carbon. Second will not be there. Am I right, ma'am?
This is our first one is this structure, right? 2-bromo pentane. And 2-bromo 2-methyl butane is this one.
First one, ma'am.
The first one is asymmetric, right? This is having an asymmetric center. Whereas this one, 2 methyl groups attached. Is it not so? When we write off
structure, 2 methyl group will be there.
Right. So this is not asymmetric. Does not have an asymmetric chiral center. Yes,
2 methyl groups are there. Yes, ma'am. 2 methyl groups are there.
Yeah, that's what. So 2-bromo pentane, na, right? That's having this asymmetric carbon chiral center. So for second one's answer will be 2-bromopentane, right?
Yes, ma'am.
And our last one there is which is the most reactive towards beta elimination reaction. So most reactive towards beta elimination, then the possibilities of giving a
Alkene.
alkene, and they're talking about most reactive towards beta elimination. So which one can go in for? Even the first one can go for a beta elimination, second one, third one, all can go for beta elimination, right?
Yes, ma'am.
So which is best among this is the question. More reactive, a better, is not, a more substituted alkene is always preferred. So which of these can go in for that? More substituted alkene possibility.
Second one, ma'am.
Second one, right? The possibility of the second one going in for beta elimination, CH3C is the Br eliminated from that and H from this adjacent carbon. Therefore, we get this possibility. So this is better. When it comes to this one, you have two possibilities, Br and H from here and H. But I think this is more substituted. Is it not, Lakshmi? What do you say?
Correct.
No?
And also tertiary carbocation will be
Is more stable. Beta elimination going in through tertiary. So this gives a more stable carbocation when Br goes off.
This is a board question, right?
Yeah, it's a board question. That's what. Resulting in a stable carbocation and then introduction. So this is preferred. Right, teachers?
Yes, ma'am.
Yeah. So then we'll just move fast. Now this again classification, just like haloalkenes, we have all these type of classifications which we'll have to give in detail to the children. And coming on to nomenclature, I just put up this slide because sometimes they give structures, give the common names because cresol, catechol, resorcinol and all is there in the text. We have to teach the children these common names also for these compounds because they can give you questions based on that. So this common names, whatever is there in the NCERT, we have to make the children familiar with that. So this trivial names to be included. Now coming on to preparation methods, we have alkyl halides converting to alcohols by treating with aqueous alkali. Alkenes by acetic hydration. So this is where mechanism, this is a chapter where we have mechanisms introduced for children. Previous chapter and all, mechanisms not important. So alkene hydration to alcohol mechanism. Then the same. So here we have, whenever it's alkene adding on water, hydration, it is following the Markovnikov's addition, is it not? Whereas when we use diborane followed by peroxide in basic medium, again it gives. So this is one, alkenes reacting with acidic hydration and use of diborane. So the difference in the product will be, just like we have HBr and HBr and peroxide giving Markovnikov and anti-Markovnikov addition, alkene to alcohol. Whenever we have a conversion where we have to get the other less substituted alcohols, we go for
Primary alcohol.
yes. If I go for propene hydration with the acidic hydration and propene with the diborane, the products I get will be, so H2O in H plus and in presence of diborane. So this is one important reaction where when we have to get two different types of alcohols there. Less substituted, more substituted from alkene. So water hydration gives us propan 2-ol, whereas with diborane we'll be getting
Propane 1-ol.
propan 1-ol, right, teachers?
Yes, ma'am.
Yeah. So we get, so that's The reaction where alkene can be converted to either of it. And reduction process of getting alcohols, again, starting from aldehydes, ketones, starting from carboxylic acid, from esters. That's very important. Process of reduction. So the reducing agents there that we use, reducing agents, most of the best reducing agent, lithium aluminum hydride. Then we have sodium borohydride. We have hydrogen, catalytic hydrogenation possible for reduction. Then sodium in ethanol. So all these are reducing agents, but some of them cannot be used for certain reactions, is it not? So aldehydes and ketones can be reduced to alcohol by any of these, is it not? So aldehydes and alcohols can be reduced by any of catalytic hydrogenation, lithium aluminum hydride, or sodium borohydride. Any of this can be used. And an easy way of telling the children, is it not? I thought time lags, we may not have time, so I've just put it on already. We can just bring in. So it's basically lithium aluminum hydride providing H minus. So we can just show the breaking of the pi bond, 1H and 1H adding. So it's basically nucleophilic addition reaction over the pi bond. So this becomes O minus, and then the second H here actually comes from a solvent part. Though for ease or for making the children understand, just break the bond and introduce 2 hydrogens. So we get RCH, HOH. So it's converting. So an aldehyde will be converting to, always an aldehyde on reduction gives
Primary
alcohol. And a ketone on reduction will be giving secondary alcohol. So ketone on reduction gives secondary alcohol. So here that will be a R, that's all. The difference is an R. So we are just breaking the pi bond, just show them introducing 2 H's, though mechanism and all we are not teaching there. The H from the hydride, the H minus comes and attacks the carbon, and it becomes CH, O minus, and then we have H plus attacking the oxygen coming in. So that's the basic method. So we'll just show this. And the second one, from carboxylic acids, we can convert it to an alcohol. So there again, there we can use lithium aluminum hydride. Sodium borohydride cannot be used. H2 cannot be used. So here again, break the pi bond, just show them the introduction of 2 hydrogens, and then it becomes like 2 OHs. So we cannot have such a compound. Remove a water, again it forms a ketone, introduce the pi bond, 2 hydrogens. So this way it's easy. So it can just show introduction of 4 hydrogens coming in. So first breaking pi bond, just remove off the water here, and then again it forms a double bond O here. So break that and introduce 2 hydrogens. So it's giving alcohol, just to make the child understand, that's all. So it's like 4 hydrogens coming in this case. Here 2 hydrogens being introduced. So aldehydes to primary alcohol, ketones to secondary alcohol, carboxylic acid with lithium aluminum hydride can be converted to alcohols. Esters, again, esters, when we show them, esters, we can use both lithium aluminum hydride and catalytic hydrogenation. So there it's like first breaking the CO bond, the SCO bond breaking, introduce 2 H's, and then break this and introduce 2 H's. So that way we can show the children how it's being converted. So when you're breaking the CO bond, we are getting the alcohol from this side, ROH, and this becomes RC double bond OH. So break that and introduce 2 hydrogens here from this part. So that is giving you this compound, RCH2OH. So this is one important thing that we should know. And in our exercise in aldehyde chapter, also we have one conversion where we cannot use sodium borohydride. So sodium borohydride cannot be used to reduce an acid and ester. NaBH4 and LiAlH4 comparison, teachers, strength, reducing strength. Sodium borohydride comes under what type? Strong or weak?
Compared to lithium weak.
Yes, lithium aluminum hydride is very strong, while sodium borohydride is not a strong reducing agent. So not for acid and ester. So we have to stress upon that. And acid chloride again, when we show the reduction, we can use sodium borohydride for acid chloride. So there again, first break the CCl bond, or say whatever, acid chloride or acid halide. So this goes out as HCl here. And then we are having a H introduced. Now second, break this pi bond and show. So H and H, another H introduced. So we get CH2OH. So this is an easy way of showing the children how H is getting into it from the hydride and all that, whatever is giving the hydrogen reduction. So adding on hydrogen there and thereby forming. So which reducing agent to be used for what starting material, all that is important. They can't just use anything for any reaction. So this is one there. So aldehydes and ketones to alcohol, so primary and secondary, carboxylic acid to alcohol. And another important reaction where you can get alcohols, which we can use for many of the conversions and all that, is using Grignard reagent coming in, Grignard's reagent. Use of Grignard reagent for the conversion to alcohol. So that's a very important reaction again here. So where we talk about the alkyl, so choice, wherever we have to prepare a higher primary, secondary, tertiary alcohol coming in. So we go in by using Grignard reagent with the carbonyl compound. So always methanol with any Grignard reagent. So the step involved, always we tell the children, no, magnesium electropositive. This is minus, so this part ionic here, and this is covalent bond. So magnesium entity carries a partial positive charge, and the alkyl part is a partial negative charge. So this is again a nucleophilic addition. So this becomes minus and plus. So alkyl group is introduced on the carbon, and we get OMGX, and hydrolysis of OMGX results in converting. So this H2O is H and OH. So H goes on to the oxygen part and OH will attach to this. So H, so this is where H introduces and Mg bonds with OH. So we are getting this compound. So always show the bond breaking, show the addition here and there. It will be easy for the child to understand. So split up the bond, add on wherever possible. So that way. So, and once they practice this reaction, a lot of conversions coming in. So any Grignard reagent with methanol leading to primary alcohol, any other aldehyde leading to secondary alcohol, and if you have to prepare a tertiary alcohol, going in for ketone. So that's one important thing coming in there. So those are the basic methods at class 12 or the NCERT CBSE level that we teach the children, these reactions for preparation of alcohols. Coming on to the reactions part, we know alcohols can be converted to haloalkanes. You can, that's by adding a lot of reagents, is not to convert to haloalkanes, which we had discussed in previous chapter also. And olefins or alkenes can be prepared by that again mechanism, is it not? Alkene preparation is by dehydration of alkenes. There the temperature criteria, all that comes in. So that is one method. Acidic in presence of H2SO4, concentrated H2SO4, 443 Kelvin. It will be converted to alkene. This is important, no? The temperature is important because otherwise alcohols at lower temperature will be converted to, what is the other possibility? If it is 443 Kelvin with concentrated H2SO4?
Yes.
It will be forming?
Esterification.
Not esterification, ma'am.
Alkene.
Ether, right?
Ether.
Ether formation comes in. And then another important part is the oxidation reaction shown by alcohol. So alcohols can be oxidized to
Aldehyde as well.
Aldehydes, yeah. Aldehydes, ketones, carboxylic acids, and all those coming in. So now oxidation, now when we come in again, we have to talk about strong oxidizing agents, mild oxidizing agents coming in. So strong oxidizing agents, what examples do you give? Strong oxidizing agents?
Potassium permanganate.
Yes, acidified potassium permanganate, right? Yes. You can go for acidified potassium permanganate, then
Acidified potassium dichromate.
yes, those are all very strong oxidizing agents, right? Acidified potassium permanganate, acidified potassium dichromate. Then we can have, what else comes in? So we can have KMNO4, H+, Yes, ma'am. Then K2Cr2O7, right? H plus. Then concentrated nitric acid, is it not? That's also a strong oxidizing agent. Then what else can we go in for? We have Jones reagent, right? CrO3 is strong, and CrO3 in presence of sulfuric acid is what is called as Jones reagent. So this is also a strong oxidizing agent. So any of these. So we use a strong oxidizing agent on an aldehyde. Strong, it will convert to
ketone or acid.
It will convert to acid, is it not? Or let me say we are talking about alcohols here. So alcohols, if we use a strong oxidizing agent, now what I've written here is a primary alcohol. So primary alcohol will be converting to the carboxylic acid on strong using a strong oxidizing agent. Secondary alcohol,
ketone.
Secondary alcohol, RCHOH, say R dash. Yes, use of strong oxidizing agent also, it forms ketone. And very drastic conditions only ketones, Popov's rule comes in, and where it breaks to, more different carboxylic acids, breaks down. Otherwise, even strong oxidizing agents, it stops at ketones. What about tertiary alcohols? Tertiary alcohols.
Alkena, ma'am.
RCR, OH, R. So tertiary alcohol. So whenever we talk about oxidation, it is you're introducing an oxygen, right? So when we are introducing an oxygen, we are introducing it to this here.
Carbon.
We'll be introducing it, between the C and H coming in. With the H we introduce. So here we have, when it comes to primary alcohols, we have 2 hydrogens where we can introduce the oxygen. Whereas when it comes to tertiary alcohols, we don't have the hydrogen, which has to be oxidized there. No oxygen introduced. So tertiary alcohols will not undergo oxidation reaction. So when you're using oxidizing agents, you're strong oxidizing agents. Now coming back to mild oxidizing agents.
Bromine water.
Bromine water. Okay. Oxidation, yes. But here normally aldehyde from alcohol, we don't go in, is it not? We don't use bromine water and all for oxidation of alcohols or such. So here,
Copper.
mild oxidizing agents, PCC, right, ma'am? Pyridinium chlorochromate. Pyridinium chlorochromate can be used. It's pyridine plus CrO3 combinations coming in, pyridinium chlorochromate. Then we have pyridinium dichromate also, PDC, which we are not using much. So this is a mild this is the one which we usually, class 12 level, what we tell children. So PCC, it will be converting to, and also the Jones reagent, if it is CrO3 in acetone, that is the mild oxidizing agent, whereas CrO3 in H2SO4 is a strong oxidizing agent. But for us, I think for children, let us just stop at PCC. So here this gives us oxidation introducing one oxygen. This will stop at aldehyde. This will go for aldehyde conversion. So this will get oxidized to aldehyde. So further oxidation only gives you acid if it's a mild oxidizing agent. And ketone will go to, for secondary alcohols, as we discussed, it goes for ketone. It goes for ketone, right? And tertiary alcohols, no oxidation. But as we're telling, there's another reagent here, is it not? Copper at 573 Kelvin. So when we use copper at 573 Kelvin, so copper at 573 Kelvin, what happens? So we can get an aldehyde ketone from primary, secondary. What about tertiary alcohols? Tertiary alcohols.
Alkene is formed.
Yes, if we
Alkene.
take a specific example, yes. CH3, OH, and CH3. Here, if we are using copper at 573 Kelvin, it goes in. Even silver can be used. Copper. So this goes in for elimination. So OH and a H eliminated. So here we get alkene. Instead of getting oxidized, it goes for dehydration, giving an alkene. So copper at 573 Kelvin, but no oxidation of tertiary alcohols. Not so that's one thing. So these are the basic things that we have discussed. So primary alcohols oxidation coming in. So as I was talking about oxidation also, like an introduction of oxygen here, we can show primary alcohols. So primary alcohols, we are introducing an oxygen. So again, when we introduce an oxygen, there are two OHs coming in here. We can tell the children not stable. So it forms again and introduce another oxygen for further oxidation. If it's further oxidation, you're introducing another oxygen here. So it becomes R, C double bond O, OH. This is how you can show the children. And secondary alcohol, you're introducing the oxygen here and then removing of water, we are getting a keton. Right? Tertiary alcohol, we don't have that, no hydrogen where we can introduce that. So that way we can just show some tactics or techniques to make the child understand. I just had this. So what will be a product for this one? These two reactions. We have sodium borohydride and we have two functional groups coming in here. Keton and we have an ester here. So we have the sodium borohydride, the mild reducing agent, which we had already discussed will not be reducing an ester group. So it will only be this one which gets reduced. So we'll have it as CH3, CHOH, right? This gets reduced, whereas the ester part is not touched. Ester part remains. So this is one example to show that reactivity. Sodium borohydride reduces only this specifically. And here I have this H plus coming in. So H plus heating. So what happens? Say it is at 443 Kelvin. If so, what is the reaction happening?
Ketone.
No, acidic. It's in acidic medium. It undergoes dehydration. We have an alcohol here. Alkene. So which alkene will be formed, ma'am? Again, we have the possibilities, not Sadzef rule coming in. When we have two beta eliminations. So this is a beta and this also beta. Both are having hydrogens. So which one will be a major product? So there can be this elimination coming in. We can have this H and this OH moving out.
Yes.
Another possibility is this H and this OH moving out. Is it not?
Yes, ma'am. 1 minute.
So, yeah.
First one. Am I right, ma'am?
Yes, yes, ma'am. Right. No, that will be the. When we talk about Sadzef rule, it's the one where you have the more substituted alkene. Again, this is called as a Sadzef product and the other is called as a Hoffman product. In some cases that dominates. Sorry, this.
CH.
Double bond, CH2. Normal cases, this will be the major product coming in. Yes. So that's one thing. Yeah. So some just thought we'll just go in. Now, another important aspect is here regarding the structure and the bond angle that we discussed with the students. So we have the normal alcohol, phenol, and comparison with ether. So when we look at the bond angles, is it not? The bond angle 108.9. Normal water, if we look in HOH bond angle, the HOH bond angle that comes in with two lone pairs. And then compared to that, when we have one alkyl group coming in, so whenever we have alcohols, it's one alkyl group and the other is H. And when it's phenol, it's H and one aryl group, and ethers are two alkyl groups. So how is it affecting the bond angle? So water, what is the bond angle in water normally? tetrahedral bond angle, our tetrahedral bond angle is 109 degrees, 28 minutes or 100.5 degree. The water, due to the presence of two lone pairs, reduces to around 104.5, right? Water's bond angle. But when it comes here, when there's an alkyl group introduced here, the bond angle is 108.9, slightly lower than the tetrahedral. Though you have two lone pairs here, still there's lone pair. So we are having the lone pair, bond pair, lone pair repulsions, is it not?
Yes.
We have the two orbitals containing the two lone pairs, which will push away, which are trying to move apart. But still, the bond angle is 108.9, almost closer to that. Why is it so? How do we compare, teachers? Methanol, phenol, and then ethers generally.
In
Why
ether,
is-
two bulky groups are there.
Yes, ma'am.
That's why it got.
So it is going beyond the normal tetrahedral bond angle, is it not? Even though there's lone pair repulsion, but the bulky groups, two bulky groups on either side are not coming closer, does not allow it to come closer. So that is overweighing. As a result, the bond angle is higher. Whereas when it comes alcohol and phenol, slight difference. Aryl group is more bulkier, is it not? Compared to an alkyl part, aromatic ring is a little more bulkier, so that repulsion felt from that, or that does not allow them to come closer. So though lone pair repulsions are acting, due to the presence of the bulky group here, that leads to a change in the bond angle. So this is more prominent because it's going beyond the tetrahedral angle, because alkyl group repulsions, two groups are not allowing the bond to come closer, not allowing, because they will be repelling, right? So this one we have to always explain to the children. Now coming on to mechanisms. The first one, as we had just mentioned about the hydration happening in presence of H plus and H2O. Formation of ethanol coming in. So it follows. So whenever the child writes, this is the most important aspect in mechanism, showing the direction of the arrows, always from electron rich to electron deficient, the bond shift. This is what we have to emphasize, because in board exams, board corrections, if the arrows are not there, they do not give marks, right, Lakshmi ma'am? Is it not? That part is important, showing the direction of bond electron sharing.
Okay. Yes.
In protonation, in preparation of alkenes, always, so what is the role of H plus? The H plus is first protonating, is it not, forming the hydronium ion, and the from the hydronium ion. So this is what, when we teach, we can show them this shift coming in, or here in this particular case, this is becoming the H2O, the H is attacking onto this carbon. This is becoming negative, this is becoming positive. So this is the shift. So H is attaching onto this carbon, and this carbon becomes positive. So first step there.
Putting the direction itself was a question.
Yeah, that's what. Correct. That's true. One
2-3
question.
years back we had a question.
Yeah, right.
Only direction, ma'am.
Only which direction? Show the electron. Yeah, direction. That was one question, as Lakshmi told.
Like only the step 1 was given. They had asked us to
Show
draw the
electron.
draw the arrow mark. That's it. That was the
Right.
question.
That's what. So first step here, formation of the carbocation, and the second step is again adding on the water molecule to it, and the third step will be the another water molecule and the elimination of this proton. So again, wherever you see, you can see from electron rich to electron deficient, the arrow direction. So this pulls out, and then this electron pair shifting onto the oxygen gate. I think mechanism and all teachers know, we need not discuss much. It's only thing, we have to talk, this is what we have to emphasize to children, that the electron direction arrow is very important. And when it comes to board exam point of view, it's always better they write it as 3 different steps and write a statement relating to that step, rather than then continue with the second step, going into the third step all together. Whenever a mechanism is asked for the board exam, they'll write it as different steps. Right, teachers? You'll just tell them to do it like that. Otherwise, when they go for higher examinations and all, I mean, other competitive, they just go and learning one to the other to the other. But when mechanism asked, they have to show stepwise with a statement. So that's very important. Sometimes otherwise they won't get full marks. They cannot score fully. So this we had already discussed. Now, another is the reactivity of alcohols. So alcohols can act both as nucleophiles as well as electrophiles. So when they are acting as nucleophiles, the bond that is breaking is the one between oxygen and hydrogen. So that show many reactions where it behaves as a nucleophile. So when it's behaving as a nucleophile, we can see what's happening. The lone pair on oxygen is what is binding on to the electron deficient species. And then the H plus is removed out. The H plus moves out. So that's how the reaction happens. So this is what is the acidic behaviors, reactions which show acidic behavior of hydrogen and all involves the breaking of the OH bond. And the second case is the protonated alcohols acting as electrophile in presence. So alcohol is first, show it separately, R is first getting protonated in presence of H plus. So again, lone pair. So whenever we show, we have to show the direction. So this one, and it is getting first protonated. So we're getting RCH2 OH2 plus with one lone pair remaining. So this protonated alcohol will now behave as an electrophile. Suppose we have a species like Br minus attacking. Now this was again 1 year's board question where most of the children went wrong. They went in for a SN1 mechanism, while this step is a SN2 mechanism. As this leaves, as OH2 leaves, Br minus attacks the carbon part. So this is a single step coming in. So this one here as shown. So this was asked for 1 year board exam and most of the children went in wrong because they went in for SN1. They removed the OH2, formed a carbocation here. They went in for the CH2R positive, and then next step they showed the attack of Br minus. So that was one case. So whenever it's as an electrophile here, this is how this comes in. So this is also important. So this involves the breaking of. So when it's behaving as an electrophile, it involves the breaking of RCOH. It involves the CO bond breaking. It involves the CO bond breaking. So when it's behaving as nucleophile, it's between the O and H. And when it behaves protonated alcohols, it is the CO bond. So if it's a CO bond breaking, first it gets protonated and then only the reaction comes in. So 2 types of reaction shown by alcohols. So the one coming in. So acidic behavior. So protonated alcohol formation, all this. So dehydration, converting. So this is one now where we have alkene converting to alcohol. We saw earlier. Alkene can be converted to alcohol by H plus and H2O. And alcohol can be converted to alkene by, again, dehydration in acidic medium. So H2SO4, alkene to alcohol, H2SO4 heating, alcohol to alkene. So both processes and the mechanism of both are important. So here it is again first step formation. So H plus helps in forming the protonated alcohol, then formation of carbocation. So ease of dehydration will be for which one? Primary, secondary or tertiary alcohol? Ease of dehydration. So all these, so alcohols, okay, converting to ether, aldehyde, ketone, alkene, carboxylic acid, ester. So ester, how do we convert alcohol to ester? Alcohol to ester?
Ma'am, shall I switch off my video because network issue and charge is also not there.
Okay, ma'am, no issues, yeah.
Thank you, thank you.
So alcohol to ester, how do we go in?
Esterification only, no, ma'am?
Esterification, yeah. We are using carboxylic acid, is it not? Carboxylic acid. Anything else can be used? Alcohol plus acid. Carboxylic acid gives ester. Then what else possibility? We can use
Anhydride?
anhydride, yes.
Acyl
We
halide.
can use,
Acyl halide also.
yes, acid halides also. Acid halides. So acid and anhydride usually in acidic medium. And when we are using acid halide, we'll be using pyridine base because HCl will be formed as a byproduct to remove out that. So this is done usually in a thick medium, and these two in acidic medium. So we can convert it to ester by either of these reagents coming in. And that is where we have aspirin preparation also, is it not? Aspirin preparation is one important example given there under ester formation coming in. So just moving on to phenols fast. Phenol preparations and reactions. Preparations we have from benzene, we have from aniline, we have from cumene. All those is not very difficult there. And moving on to reactions of phenol. So this reaction with sodium hydroxide. Reaction with sodium hydroxide shows what nature of phenol?
Acidic nature.
Acidic nature of phenol. And many of the reactions where phenol is first converted to sodium phenoxide and then the reactions happening. So with sodium hydroxide giving sodium phenoxide, with sodium metal it gives sodium phenoxide. It can react with sodium hydride, sodamide, all that to give sodium phenoxide. And then particularly sodium dichromate and sulfuric acid to prepare benzoquinone. And phenol to benzene using zinc dust. And here we have two name reactions coming in, is it not? The phenol can be converted, yes, salicylic acid by Kolb's reaction, and Riemer-Tiemann reaction gives salicylaldehyde. So when we are using chloroform and alkali, it is forming salicylaldehyde. If we use carbon tetrachloride and sodium hydroxide, it will form salicylic acid like Kolb's product. But for our CBSE level, they have not given that. It's only this one where it forms salicylaldehyde. And the intermediate compound that attaches there is dichlorocarbene. Sometime I think some MCQ or somewhere I've seen this. What is that which attaches? It's dichlorocarbene from chloroform, which forms
Dichlorocarbene.
Carbene, dichlorocarbene, CCl2 with a lone pair on carbon. We don't have the mechanism, but still. Now coming on to nitration, phenol nitration is not, we get, when we use dilute nitric acid, we get a different product. When we use concentrated nitric acid is a different. So dilute gives us monosubstituted product. Ortho and para, with para being the major product, whereas concentrated gives us
Picric acid.
picric acid. That name is again, no, common name picric acid is be known by the children.
Yes.
And bromine, when use carbon disulfide as a solvent, we get monosubstituted product. Whereas if we want tri-substituted, we go in for aqueous bromine, right? Bromine water. So these are the main reactions coming in for phenol there.
Yes.
Yeah. Now the main thing again here is the acidity of alcohols and phenols. So when we look at alcohols, what can we say? Are they acidic? Alcohols, acidic nature.
Yes.
Alcohols are acidic in nature, but is it strong acid or weak acid?
Compared to phenol, it is weak.
Yes. And compared to water?
It is strong.
No. Alcohols are weaker than water. Alcohols are weaker acids than water. If I have the alkoxide ion plus water, what is going to happen? Alkoxide ion plus water. Which is preferred? ROH plus OH minus? Which
Yes,
one?
ma'am. Alcohol plus OH minus.
ROH and OH minus. Which possibility, proceeding in which direction is possible? So if you say this, if I write it, it should be RO minus and H2O, right? This is what? This is not favored. This is what is favored.
RO minus will be an unstable anion.
Yes. So what we get here is, again, this one is giving out. So we'll have it as ROH and OH minus. What I wrote there, it's a reverse here. So this is a strong acid. And the corresponding base formed here, this is weak, the conjugate base. And here you're having the base here. And this acid is weak conjugate acid coming in. So when we have alcohol and water, alcohol is a weaker acid than water. Are you getting with ma'am? But there is one exception, methanol. Methanol is more acidic than water. Methanol is more acidic than water, but all other alcohols are less acidic than water. So this is the equation related. Yes, ma'am?
Yes, ma'am.
Yeah. So this always water will give out a proton to alkoxide ion. The other way around, this is not alcohol giving out a proton to OH minus to form water is not very feasible. This is what is feasible. So alcohols are weaker acids than water, whereas one exception there, methanol is more stronger.
Okay.
That is why if we take sodium hydroxide, methanol can react and replace, whereas ethanol and all will not. So this is one, okay? It's a comparison. And when we talk about the acidic behavior, primary, secondary, tertiary acidic behavior, if we look in
Primary will be more.
primary,
2 hydrogen atoms are there attached to the
2 hydrogen atoms are there. Secondary is
only
2
one.
alkyl groups. And tertiary is where we have 3 alkyl groups coming in. So acidic behavior is the ease with which it moves out as a proton, is it not?
Yes.
So in this case, so most acidic,
Primary.
primary. The reason for that?
It can easily look because
only one alkyl group, that's why we
Is that.
do only one positive I group, ma'am.
Yes, right, sir.
But
One plus I group. Whereas 2 plus I groups, and here 3 plus I groups increases the electron density on oxygen from this side. So the OH bond will not be polar, right?
Yes.
Lot of electrons being pushed towards oxygen from this side. So oxygen is electron dense by itself. It need not take away the electrons from here. So primary alcohols are the most acidic compared to secondary and tertiary alcohols. And then comes our comparison with the phenol and alcohol.
Phenol is more acidic than alcohol.
Yes. How do we give that explanation to children?
Phenoxide ion
Yes, ma'am. Yeah, phenoxide ion.
stabilized by resonance.
Yes. So in this case, we have the plus I effect coming in. So the oxygen electron density on oxygen. So if we look at the resultant, yes, as you told, the alkoxide ion and the phenoxide ion. Yes. So alkoxide ion is stabilized. So what is the reason for that? So resonance. And how this is also having resonance, is it not? Phenol is also having resonance. Then why do we say that? Phenol is also resonance stabilized. Phenoxide ion is also resonance stabilized. So why do we say phenoxide is stable?
Lone pair of electron on hydrogen. Sorry,
Yes.
on oxygen.
Lone pair.
Delocalization of that electron.
Yeah, here also we have this movement of electron here and negative charge. So when it comes to phenol,
Yes, ma'am.
one of the structures is, if I draw, it will be O plus, right? And this is minus. So one of the resonance structures. Whereas here, if I show the resonance, what is going to happen? Double bond O. Sorry, I forgot the double bond. Double bond O
Negative here.
and negative charge here, the remaining two here. So what is the difference between the structures of these two? The phenols for one resonance structure and phenoxides and a resonance structure. And when we draw the resonance, both are having 5-5 resonance structures, is it not?
Yes, ma'am.
But phenol is not stable. Phenoxide ion is stable. That is why it gives out H and forms phenoxide ion. So both are resonance stabilized. So then what is the difference there? How do you explain to your students? When it comes to this, how do we explain the difference? So that means the resonance of resonance structures or canonical forms of phenoxide ion should be contributing more to stability, is it not? Compared to that of phenol.
Yes.
So what is the difference when we see these two structures? Sir, also if you could participate.
There is no positive charge when it comes to phenoxide on oxygen.
Yeah.
Whereas on oxygen, there is a positive charge if the resonance
In
is
phenol.
Yes. So yes, that's what now, ma'am. That is here. There is a charge separation in all of the intermediate structures where we have the shift of electron pair, positive and negative charge. Whereas in all the phenoxide structures, there's only negative. Oxygen does not carry a positive charge, right? So if there is a charge separation in any of the canonical forms, when we talk about the different stabilities of canonical forms, charge separation leads to it being less stable. So in phenoxide ion, no charge separation in the canonical forms, whereas in phenol, the canonical forms have charge separation. All the second, third, fourth structures will have plus, minus, isn't it? When it comes here, when it comes here. Whereas here always it is, the oxygen does not carry any charge. So no charge separation. That is the reason why phenoxide ion is more stable compared to phenol.
Yes, thank
So
you.
that's how we have to explain to the children. So alkoxide, phenoxide. Phenol is having same resonance as phenoxide, but still, why is phenoxide ion stable and not phenol? No charge separation in the structures. So that one point there. So comparison of alcohol with water, comparison of alcohol with phenol. The other one will be substituted phenols. So substituted phenols. Now pKa value is given. This is from our textbook data there. So pKa value is given. So higher the pKa, lower will be the lower will be the acidic behavior, right? So we have the 115.9 here.
In ethanol.
As we discussed very clearly, alcohol, ethanol is a very weak acid as shown by its pKa value, right? Whereas when it comes to phenol, this is 15.9, this is 10. So it is more acidic compared to ethanol. So compared to ethanol, more acidic. And now we have this here. We have nitro substituted phenol and here it is cresol. So cresols are nothing but methyl substituted. So nitro, we are having electron withdrawing group here, and in this set we are having electron releasing groups. So how are they affecting the acidity of phenol? That's another question which comparison comes, arrange in decreasing, increasing order. Mostly it can be paranitrophenol, paracresol, and phenol asked. So in that case, so paranitrophenol.
Electron withdrawing group, polarity will be less, am I right, ma'am?
It will be, so when we are having electron withdrawing group, It's pulling away the electrons, is it not? From the ring and this. As a result, the electron density on oxygen will so when we have orthonitrophenol,
Decrease, ma'am.
acidic behavior,
Less polarization will occur. Acidic behavior will decrease.
is it so, ma'am? Because nitro group is electron withdrawing. So if I in turn keep on showing this arrow, it's pulling away the electrons. So oxygen's electron density decreases.
So H will be easily removed, no?
It will be easily removed, is it not? Because of the so electron withdrawing groups present, especially at para and ortho positions, will be increasing the acidic behavior. Whereas
pK value will be more.
pK value will be pK value is inversely proportional to the acidic behavior. So more acidic, lesser pK.
Yes.
Right? And when it is methyl, methyl is an electron releasing. So it's pushing electrons towards oxygen. So electron dense. So it will not have a tendency to make the OH bond much polar, is it not?
Yes, ma'am.
So it will be less acidic. So whenever electron withdrawing groups are there, it makes it more acidic. And phenol without any other group comes intermediate. And this will be electron releasing group will be least acidic. So with that in comparison, we can see, is it not? Crisols are 10.2, 10.1 and all. Slightly pK value is higher compared to phenol. That means less acidic, right? Compared to this.
Yes, yes.
And these are having higher, lower pKa value. That means more acidic. And ortho and para is more prominent. Meta, when you have nitro, so that way you can see 8.3, not affecting much because OH, ortho para is where you have the electron density coming in. So slight difference. So whenever electrons, so this from this part, more important is the comparison of presence of electron withdrawing group, electron releasing group, and absence of any of this. How do you come in for this? So again, we have to give all possible commonly asked electron withdrawing, electron releasing groups to the children. They should be very thorough about that.
They are asking question under this, no, ma'am. Decreasing order, increasing order, acidic strength.
Yes, ma'am. Yes.
In compounds.
Yeah. So this type of questions can be asked. So the child should be knowing all common electron withdrawing, electron releasing groups and all that.
Yes, ma'am.
Right. So basically, so all the elimination, we don't have time to discuss in detail. So we had just touched upon all those. Now moving on to the last part of compounds, the ethers. So preparing ethers, we have two methods, right? So one method of preparation is from alcohol. So that is what we just were discussing when we took about, it can be into alkenes or into ethers depending on the temperature. Sulfuric acid presence at particular temperature, it goes in for ethers. And this method is particularly suitable only for symmetrical type of ethers. We go in for this method mainly for symmetrical ethers, not for the other unsymmetrical type and all. So again, so here the mechanism, how is it different from that of alkene? So in the first step is the same for both alkene and ether preparation. First step is the protonation of the alcohol. Second step is where it differs. In the case of alkene, what is the second step?
Nucleophilic attack.
This will move out, is it not? In the case of alkenes, this moves out and you're having a carbocation being formed. Whereas now here you can see this is a single step reaction. As the protonated H2O part leaves out, another molecule of alcohol attacks. So here we have two molecules participating in the mechanism. So first is protonation of the alcohol, and as the protonated part, the oxygen moves out, another alcohol molecule through the lone pair on oxygen is attacking the carbon, which is going to become positive because this is moving out. The bond pair is moving out, so it's becoming electron deficient. So the lone pair attacks onto this. So that way we are getting the second step where we have a compound with an extra proton here. Protonated compound is formed, and the third step will be the removal of this. The proton is moving out and thereby oxygen gets back its lone pairs. So this is the mechanism for alcohol getting converted to ether. So two children should not be confused. So alcohol to alkene mechanism, alcohol to ether mechanism. So suitable for preparing symmetrical ethers. When we go in for unsymmetrical ethers and all, the main method of preparation of ethers is Williamson synthesis. So Williamson synthesis uses an alkyl halide and alkoxide. So alkoxide is important here. So the choice of reagents. So if I have to prepare CH3, OCH3, I have no confusion there, is it not? I can take chloromethane and sodium methoxide, starting from that, no problem. Whereas the example given here, if I have to prepare CH3 thrice OCH3, what should be my starting material? So what will be our Rx and what will be our sodium alkoxide that we have to choose? Again, is it just, can we go in for anything? Can I have it as CH3 thrice CX and CH3ONA? Or can we have it as CH3 thrice CONA and CH3X? Can we have it both way, any way around? How do you all emphasize about this part? Children always get confused about this one. Here, ether preparation for this as well as reaction with HI. So what is the choice here that we have to?
First one, I think, ma'am. First one.
First one. Why is it the first one, sir?
Because the CH bond is polar due to high electronegativity of halogens, ma'am.
Okay.
That can be easily removed as X minus.
So, but sir, if we go in like that, like yesterday we were discussing about the presence of a strong base coming in. Sodium alkoxide is a strong base. So whenever we have a strong base, it will result in a tertiary haloalkane with a strong base. It will go in for what? This will result in, the choice is not correct because it will result in
Elimination. Dear.
Elimination. So we are going to get an alkene here. We get an alkene here. So this results in an alkene. So we cannot choose this combination. This combination is wrong. So whenever we have a tertiary part coming in, this is a tertiary and a primary, always the tertiary part will be your alkoxide. Your starting material when you choose, the tertiary part should be the alkoxide, the tertiary one. And the other primary or secondary, that should be the haloalkane part. So this will be your X part and this will be your ONA part. So this is how you can start. You can try. So what should be this? And from this, you can go and start your starting material. CH3 thrice, CONA will give you plus this. Yes, this is very important. This one, you can see if we choose alkyl, tertiary alkyl RX, it will result in alkene. Whereas tertiary is your alkoxide, then it will result in an ether. So very important, where always the children have a confusion there. Is that okay, teachers?
Yes, ma'am.
And another important thing is this one, no? Whenever we have to have a ether with a phenoxide part. This one. So what is going to be our starting material? Again, can we have any combination? So can I have my X here? Sorry. Can I have the X here and ONA here? Or do I go for, what do you say, X here and ONA here? What do you think? Which one? Do I start with do I start with ONA and RX to prepare this, or do we start with X and RONA? Can we go with any other? Can we go with any of the combinations?
First one, ma'am.
First one. This is not possible. If not, why not? We have to explain, isn't it? We have to tell the children why is it not possible. So we say this and this part is not possible. This is not, why is it so?
Because
What explanation?
lone pair electrons of halogen can be involved in resonance, ma'am.
Okay, sir, yes.
So it is not easy to remove that X from this RX.
Yes.
That is
CX bond, as usual, we say this bond is having partial double bond character. So, yes. Involved in resonance, the CX bond, we can talk about partial double bond character. So, the cleavage of this bond is very difficult. So, always when we have a phenol ether with a phenolic group, I mean C6H5 group coming in, always this will be our starting material. RONA, and this one will be our choice. Alkyl part will be the choice of halide. So these are the two things which you have to emphasize, give importance, give examples to children while talking about preparation by Williamson synthesis. Right, teachers?
Yes, ma'am.
Yeah. And now when coming on to the reaction shown by ethers, the reaction that we have is the reaction with HI, ethers with HI, right? So ROR with HI. So when this happens, the reaction is, now I have shown a symmetrical ether. So symmetrical ether, I can show one of the OC bond breaking. I can add a H here, I can add a I here. So that's going to give
Alcohol and
ROH and RI. This is fine. So this is it. And if we have excess of HI, if the reaction is excess of HI, so what is going to happen?
Alkyl halide only produced, ma'am. Alkyl halide only.
Another alkyl halide. This one will also be converted to RI. It is like, it can be like another H here and another I here. So I'll be getting 2 RI and say H2O. So this way we can show if it's excess, that is it. Excess for symmetrical or unsymmetrical, both are being will be converted to the iodide coming in. Only if it is a limited amount of HI, the choice of, again, the product when it is coming to a limited amount of HI, what is the suitable product coming in? So that's what we have to look into. So if I am going in for an example of, say, CH3O, CH2, CH3 with HI.
The oxygen goes with a smaller alkyl group, ma'am.
That's the first, right, as you're saying, sir, first step is H coming in, is it not?
Yes, ma'am.
H will be introduced. So we are going to have CH3, H with a positive charge on oxygen, CH2, CH3. Now the second step, so after this, so when if mechanism, they have to write a second step. Now I'm just writing it here itself. Second step. The first step is forming this. Now second step, if I show, is this one here. Follows SN1 or SN2. Mechanism followed. SN2, SN1?
SN1, ma'am, because two step.
This is primary, this is also primary. So when that comes in, it goes in for a SN2 mechanism. SN2 mechanism. So when it's an SN2 mechanism, I minus should attack simultaneously. So where does it attack? CH3 or CH3, CH2?
CH3.
No, less hindered. CH3 is less hindered. So the attack will be, so this will move out as, so you're going to have a bond breaking here. Thereby our I will come and attack here. So I will come here. So what are we therefore getting? We get CH3I and ethanol, CH3, CH2OH. So whenever it's all primary groups and all coming in, it will be less hindrance coming in. It will always go in by an SN2 attack. Yes, teachers? So
Yes,
it
ma'am.
will be the iodide part will be attacking the less hindered alkyl group. So we get the iodo compound will be the one with smaller alkyl part, and the alcohol will be with the higher. If it's excess, this will also be converted to CH3, CH2I. So no problem there. So that's one. Now suppose I have this one. If this is our compound, just like we saw for preparation, if I have a compound like this, an HI reaction. So in this case, how do we go about? Anyway, in all the cases, first step is the same. First step is the protonation coming in. So O. So what are we getting here is, we get it as CH3 OH plus CH2 CH3. Now the second. So I'm
Second
now
step,
going to
minus will be attached to the ethyl part, CH2, CH3 part.
ethyl part. Yes, ma'am. So why do you say it's to the ethyl part now? So now, ma'am, you have to see in.
Three.
This is tertiary. This is primary.
Primary.
Okay. So whenever there is a tertiary part to the ether, the mechanism that is followed is SN1. Because there is a possibility of, it's a tertiary group there coming in. So that way it will always prefer SN1 mechanism. And SN1 is by carbocation intermediate, right?
Yes, ma'am.
That means there's going to be a split here now. There is going to be a bond breaking here now. So we are going to have, so the, which one will leave out?
Tertiary butyl alcohol plus ethyl iodide.
Yeah, these are the two possibilities, is it not? If this is breaking, I'm going to get this as the carbocation. Whereas if this breaks, I'll get this as the carbocation. So which is preferred? Tertiary. So whenever we have an tertiary coming in, it follows an SN1 mechanism, and therefore we are going to get a tertiary carbocation in this step, and ethanol moves out. Right? And then the last step will therefore be the introduction or the coming in of I minus. So this is again what we have to be careful about, right? So whenever there's a tertiary in the ether, we have questions like that in our textbook. So when it is tertiary, it will be following SN1, it goes through a carbocation. So tertiary is your stable carbocation. Therefore we get, when there is a tertiary group, alkyl iodide here and H here. Is that clear, teachers? This will be I here, H here. And one more last thing coming in is when we have phenol ether. This one as the ether. OCH3 plus HI. So here, where will our H go? Where will our I go?
Phenol plus methyl iodide, ma'am.
Possibility is either this breaking or
This break.
this breaking. So which can break?
That one will be break. OCH3 bond.
OCH3. This cannot break. Now we just saw now the partial double bond character. So this will not break. Therefore our H and I. So I will. This will bond to. This will bond to I. So we are going to get phenol and
methyl iodide.
Methyl iodide. So whenever always this is a C6H5O, always one of the products will be phenol and the other only will be converting to iodide. These are the important ones in the chemical reactions coming in. So when this is it, it follows an SN2 mechanism, primaries and all that. Whereas when it's a tertiary coming in, it will follow a SN1 mechanism. And when it is a phenolic ether, always one product will be phenol. These three you have to always teach the children so that they understand properly. Can we just be fast with these products now?
Methanol and ethyl iodide.
First one will be methanol and ethyl iodide. Ma'am, is it so? Because which is our So it's following what mechanism? It's following SN2 mechanism. So simultaneous attack. So first H would have bonded here. So which one, where will I go? So as I will go to the less hindered site.
Sorry, ma'am.
No?
Methyl iodide.
So it will be forming, yeah, CH3I here and Hs. CH3I and CH3CH2OH. Yes. Now second one.
Second one, methanol and butyl iodide.
Yes, this one, tertiary butyl, no? CH3OH. So this is what will break because this is following a SN1 mechanism. So we get a carbocation. So we get CH3 thrice Ci, right? Now the third one, we have a primary and secondary. So it will follow again SN2.
So methyl iodide and secondary alcohol.
Methyl iodide, yes ma'am, right, correct. Less hindered, so that is it. Now this one we just discussed now. So what are we getting?
Phenol and methyl iodide.
Yes. And the last one here. That is our textbook exercise. I think we have a question, same or similar.
I don't know. I think methyl iodide and benzyl alcohol.
Methyl iodide and methyl alcohol.
Benzyl alcohol.
Benzyl alcohol. Sir, could you also? Sir there? Prabhakaran sir also? So we have a possibility of two bonds breaking here. Either it should be this one or it should be this one.
This one.
And wherever, as we had discussed here, tertiary, whenever there's a possibility of a formation of a carbocation, stable carbocation, we have to immediately think on those terms. Though this is primary, but it is a benzyl group. If you look at that, so when we have this H plus which is formed here, whether it will follow an SN1 or an SN2 mechanism here.
SN2.
SN2. Ma'am, just think. If I go in for an SN1, just think in that way, ma'am. SN1 if we go in. Is there a possibility of carbocation? One possibility is this as a carbocation, another possibility is this as a carbocation. Any speciality there? Any speciality here?
Benzyl group, phenyl group is there.
Carbocation.
Benzyl carbocation. This is methyl.
Benzyl carbocation, do we say it is stable, ma'am? Benzyl carbocation is stabilized by resonance. Okay. This forms a benzyl carbocation and it is stabilized by resonance. So in such a case, it will be following a SN1 mechanism. So when it's following an SN1 mechanism, therefore,
I will be here.
yeah, it will be forming CH3OH and
Methanol and benzyl iodide.
yes, benzyl iodide. So this is another question which is a little, different where the child may get confused. So this also we have to give importance. So this ether part, quite a lot where the child has to understand, not undergo confusion. So preparation, we have to take clearly Williamson synthesis, and we have to go in for another session where we have to separately explain with HI and all these different reactions.
Allylic also, no, Sindhu? Similarly. And allylic, where
Allylic
is involved also, allylic.
Allylic also, yes. Even if it's allylic, the same carbocation. If we have this, something like this, no, in this case also it will be following the same, right? You'll be getting this part as your iodide, because that also is resonance stabilized. So wherever there is a possibility of a stable carbocation, this comes in.
There is attachment of the halide.
Yeah, and we have to look at formation, and iodide will always attack only that. So we can have questions like this for children. I don't have time. We have crossed. And one more thing before leaving. So all this was there. No time for all this. We'll maybe just put. This is another exercise question which we have to give importance. No description in the part there. So this one, teachers, just 2 minutes and we'll wind up. Here, how about this one? Addition of HBr. First step involves protonation, is it not?
Yes, ma'am.
So when it goes to protonation, we are getting OH2 plus and this. What about the next step, Br minus attacking? So next step will be removal of this, right? So we are going to get a
CH3
CH plus CH3. So what is our product finally? HBr addition. It should be giving. So Br, next step is attacked by Br minus. So what are we getting as the product? The question already gives us the product. The question already gives us the product. So normally if I go in this way and then I attach my Br minus here on the CH plus, I am going to get 2-bromo-3-methyl butane. But the product given is not that. Because the product is given, we have to think, is it not? If the product is not given, the child may go wrong. He'll immediately put it this way.
Yes.
But why is the product that one? If you could just fast, we'll wind up. I have taken 3 minutes extra.
No problem.
Yeah, ma'am. So here, this is a carbocation, but why is Br minus not attacking here? But we are seeing the product is on this one. Br is coming on this one, not here. Why is it so? So this is where in the content of the text, yeah, ma'am?
Inductive effect, ma'am. CH3.
No, we don't say it's not an inductive effect, and this is not explained in the content part, is it not? So whenever we have a possibility, now if I have, instead of plus coming here, now this is a secondary carbocation, whereas if I'm going to have a plus on this one, what is it going to be? If it is going to be this CH3 plus CH2CH3, this will give a tertiary carbocation, is it not? So a tertiary carbocation is more stable than a secondary carbocation. And how can that happen? If I just shift the H here, the hydrogen on this carbon is shifted to this one. So they are on adjacent positions, 1 and 2, right? If you look at, they are on adjacent positions. So when we are doing such a shift, it's called as 1,2 hydride shift.
What
So it can be a hydride, it can be a all the three were methyl. I can also shift a methyl group that side. It will be called as 1,2 methyl. So if there's a possibility of a stabler carbocation formed by this rearrangement, it will go for it. So this one goes for a rearrangement to give a tertiary carbocation, which is more stable. And that will then be attacked by Br minus. And that is why we are getting
this product.
This as the product. The content does not talk about any hydride shift or methyl shift, anything. So we have to give the child about this idea. We have to explain it and then go in for the solving of this one. Like, this is an example of 1,2 hydride shift. We can have 1, 3, all that more. So this is one question, the last question in the exercise there. So I just thought we'll put it up here.